In this video, we're going to define what it means to diverge to either positive infinity or to negative infinity, and then we will look at a quick example that will prove that, prove one of those. All right, so diverging to positive or negative infinity. A sequence S sub n is said to diverge to positive infinity, and we write that that limit is equal to positive infinity, provided that for every single choice of m in the real, there exists a natural number n such that whenever we are further along in the sequence, then our sequence value is going to be larger than m. Right? So no matter what real number you come up with, there is a value in the sequence. Once you get far enough down, all the values in the sequence are going to exceed that value of m. And you can say a similar thing to when it's diverging towards negative infinity, right? And so as we diverge towards negative infinity, we say a sequence diverges towards negative infinity, and we write it in this way. If for every choice of m in the real numbers, there's a natural number n such that whenever we are far enough along in our sequence, then our terms are going to just keep getting smaller and smaller. Every term in the sequence after a certain point will be less than whatever real number you might choose. All right, so let's use this definition to prove that the limit as n goes to infinity of 5 times n is actually equal to positive infinity, right? And so like that intuition is pretty natural there. But how do we go about proving this? And so here is our proof. So we need to let m be a real number. Then we could let n be equal to m over 5. If we do this, then for little n bigger than n, which is m over 5, we will have 5n is greater than m, right? So the terms of our sequence are going to be larger than m as long as we're far enough down. So as long as we're more than m, as long as our index for the sequence is more than m over 5. All right, and that's the proof. That is it. Nice. All right, so how did we prove it again? We went through and we started with a very arbitrary choice of a real number, because this needs to be true for every choice of real number. We can build this value of n and says no matter what choice of that real number you might have, if we choose n in this way, then whenever we have little n bigger than this, we're going to end up with the terms in our sequence right here being greater than m. Right? And as you might imagine, there's some like background scratch work that went on before writing this, right? So we don't just kind of magically come up with m over 5. We really kind of over to the side in our mind or in some scratch work, we said, okay, we need to have 5n be bigger than m at some point in time. Divide both sides by 5, so we need n to get bigger than m over 5. Oh, that's the choice that we are going to make for our value of n up here. Right? And so we did that in scratch work, so that blue stuff right there would be considered scratch work. But that's what we did in the background to identify this choice right here. All right, I will talk to you next time.